At the apoapsis, the object should be slower, and at the periapsis, the object should be faster. So we're gonna fix it in a moment. So let's just start with the physics part. We should now define the speed of an orbit. Okay, the speed of an orbit, v, is the square root of 2 mu times 1 on r minus 1 on 2 a. Okay, what does this mean? Okay, what is mu? Mu is the planetary constant of gravitation, and it equals g, which is the universal gravitation constant, times the mass of the planet. But we don't know the speed at which we are moving. We just change the angle. So what we're looking for now is actually delta alpha. Okay, how do we find delta alpha in this thing here? Okay, let's start with some demonstration. Okay, we know that speed equals space divided by time. So speed equals delta space divided by delta time, because the speed could be defined as the variation of space in a variation of time. Okay, so let's now draw our ellipse. This is our ellipse. Okay, let's draw the plane. Okay, we don't know the speed, we don't know delta space, we know delta time. Okay, and delta time is just what we call in Unity time dot delta time. Okay, how do we know the space? Well, let's just draw a point here. Okay, this is our angle, and this is the space. Okay, this thing here is the space. Okay, how do we find this space here? Well, the real answer to this question involves calculus, but we want to simplify the thing as much as possible. So we're going to try to find the space with a proportion. Okay, we know this angle, we know that the whole angle is 360 degrees, so we know that alpha divided by 360 degrees equals s, which is the space, divided by the whole perimeter of the ellipse, which is p. Okay, how do we find p? Well, the answer to this question involves calculus again, but we want to approximate the value as around 2 pi square root of a squared plus b squared divided by 2. So we want to consider it something like a circle and consider the radius as the geometrical average of the semi-axis. Okay, this is actually a rough approximation, but for near circular orbits it's not going to be a problem at all. So we defined a rough approximation of the perimeter. So we have the perimeter, we have the angle, now we have space, or at least we have something which is pretty close to the space. So let's just find the space. Okay, this is the space. Okay, so let's just say that v equals delta space, which we just found, and is p times alpha divided by 360 divided by delta time. Okay, p times alpha divided by 360 degrees divided by delta time equals 2g m 1 over radius minus 1 over 2a. Radius is actually the distance. This is actually delta alpha. Okay, what we want to do now is leave delta alpha here. So we're gonna throw the perimeter down here, and these two here, 360 delta t. Delta alpha is 2g m 1 on r, 1 on 2 a, divided by p, which we said is 2 pi square root of a squared plus b squared divided by 2 times 360 delta time. Delta alpha equals square root of 2g m 1 on r minus 1 on 2a times 180 delta t divided pi a squared plus b squared divided by 2. So this is the final low. So delta alpha now equals okay, so we're done. I translated the whole thing, and I just realized that this whole model here wouldn't care about your rigid bodies. So at the end of the video, we're just gonna try and adapt the model to be used with rigid bodies in case you want to do something Kerbalish. Okay, so I've been playing around with the values a little bit, and I added a random G and M just to try. If you want, you can add the real G and real M. You can make your system as much realistic as possible. This thing is just from another universe. Just don't care about it. But what I want to demonstrate here is that the actual speed changes, and it's slower at the apoapsis, and it gets faster when it reaches the periapsis, and I'm pretty satisfied with my system right now. And when I tried to play, there were some errors because I had to add a little bit of absolute values to the square roots. So when you have errors and square roots, just add absolute values, and it's better if you know what you're doing. But if you're tired or lazy like me, just add a couple of absolute values and it's all gonna be okay. And then after your system is working, if you have a look and find out what's wrong with it, yeah, I think it could be a good idea. And now it should look like an actual planetary system. The small satellite is orbiting the big satellite, and this body here is static. I could actually make it orbit around a bigger one, and I think it's pretty realistic. Let's talk about Unity physics now. If we add like, let's say, cube with a collider and all, the bodies here are going to totally ignore it. Okay, what we want to do now is transform that position with rigid body dot move. So we want to add rigid bodies to the bodies. Okay, no gravity. We just created our own gravity, and let's just copy the rigid body and paste it here. As you can see, there are two values of the mass. Yeah, we could actually make a get component and take the mass here and take it here, but we just don't care about it now. You can do it yourself, because if you're able to do what I'm doing now, you can use a get component, I guess. So let's just add a rigid body. Let's call it RB, and let's just say that RB equals get component rigid body. Yeah, let's just transform that position to RB that move position actually. Okay, if we apply the thing and do it again, let's just wait for the encounter. We could go it this way, and yeah, we moved the object. So now we have physics. Okay, thanks a lot for following this lesson, or lessons actually, because I think I'm gonna split the video since it was like 2 hours of recording. If you have any suggestions or requests, just write me in the comments, and yeah, goodbye.